You know, every single time you flip a switch, or charge your phone, or heck, even get an MRI scan, you are tapping into a fundamental principle of physics that was discovered almost 200 years ago. It's wild, right? Today, we are diving deep into Faraday's law of induction. This is the discovery that literally powers our entire world. And this whole explainer is based on a really fantastic essay by Georg O. Schneeppot.
Welcome to our quantum deep dive. And yeah, it's funny, Faraday's discovery was completely classical, 19th century physics. But what's so cool is that we're going to see how that very same spark eventually lit the fire for the entire quantum frontier.
All right, so let's set the scene. We're going back to the early 1800s. At this point, physicists had figured something out that was pretty groundbreaking. An electric current could actually create a magnetic field. But, as it often happens in science, that answer just led to an even bigger, more elegant question. And the question was just so perfectly symmetrical. If electricity can make a magnetic field, well, can a magnetic field turn around and create electricity? It seems obvious to us now, but back then, it was a huge puzzle. And solving it? Well, that was going to take a really special kind of mind. Someone who just didn't think like everybody else. And that person was Michael Faraday. And what's just so incredible about Faraday's story is that he wasn't some academic elite. Not at all. He was the son of a blacksmith, had zero formal education. He basically taught himself everything he knew about science by reading the books he was supposed to be binding as an apprentice. I mean, can you imagine? His pure, raw genius is what got him a job as a lab assistant, and that's where, in 1831, he made the discovery that would change the course of human history. So what was this massive discovery? It's called Faraday's law of induction. And I want to be super clear here. This is not just some dusty old formula in a textbook. No way. This is the seed. It is the single conceptual seed from which our entire modern electrified world grew. Okay, so to really get his law, we have to talk about something called magnetic flux. It sounds complicated, but it's not. Just picture this. You've got a loop of wire. The magnetic flux is basically a measure of how much magnetic field is passing through that loop. The hula hoop in the rain analogy is perfect. The flux is how much rain is going through the hoop. But here's where Faraday's genius comes in. It wasn't the rain itself that mattered. It was when the rain started or stopped. It was the change in the flux that held the secret. And he proved it with his brilliant and now famous experiment using an iron ring. So he had two separate coils of wire wrapped around this ring, not touching, and what he saw was mind-blowing. When he flipped the switch to send current through the first coil, he got a tiny brief surge of current in the second coil, and then nothing. As long as the current was steady, the second coil was dead. But the moment he turned the first coil off, bam! Another little surge. That was it. The big insight: a steady, constant magnetic field does absolutely nothing. It's only a changing field that can create electricity. So this incredible observation gets boiled down into what we now call Faraday's law of induction. And if you strip away all the jargon, it's actually really simple. The faster you change the magnetic flux going through a loop of wire, the more voltage you're going to create. It's that direct. More change equals more power. Period. And here it is, the famous equation itself. Now that d phi b dt part, that's just the fancy math way of saying the rate of change of magnetic flux. But I really want you to focus on that little minus sign at the front. That thing is so important. It represents something called Lenz's rule, and it basically says that the new current you create will generate its own magnetic field that fights back against the original change. Nature pushes back. Without that minus sign, you'd have a perpetual motion machine, free energy. It would break the laws of physics. That little minus sign is what keeps the entire universe in balance. Okay, so what Faraday did was just a masterpiece of hands-on experimental physics. But his law was all described in terms of things you can touch: circuits, wires, coils. The next giant leap was to take this observation and turn it into a universal truth, something that described the invisible fields themselves everywhere in space. And that monumental job fell to one of the greatest minds in physics, James Clerk Maxwell. Right, and Maxwell's genius was basically in translation. He took Faraday's law, which you can think of as an integral form. It looks at the big picture, the whole circuit, and he translated it into a differential form. That means it describes what's happening at every single individual point in space. So we go from Faraday, talking about voltage in a wire, to Maxwell talking about how fields behave in the empty vacuum of space. It became a truly universal law. And this is it. This is Maxwell's version. Don't get hung up on the symbols, just focus on what it's saying because it is profound. It says that a changing magnetic field, that's the right side, creates a swirling, curling electric field on the left. And this right here, is the engine of light. This is how an electromagnetic wave can travel through empty space forever. A changing B field makes an E field, which then changes and makes a B field, and on and on and on, leapfrogging through the cosmos. So from this one beautiful, elegant law, an entire forest of technology just exploded into being. And I'm not exaggerating here. You can trace a direct line from this single principle to almost every single piece of our modern, plugged-in world. Just think about it for a second. The huge generators at a power plant? That's just spinning a giant coil of wire inside a magnetic field. The transformers you see on power poles? Faraday's law. The electric motor that powers your car? Faraday's law, just in reverse. Even super modern stuff like wireless charging for your phone and MRI scanners in hospitals, it all comes straight back to what Faraday figured out in his lab back in 1831.
And let's just talk about the transformer for a second. It's such a simple, elegant device, but modern ones are just astonishingly efficient. Like over 99% efficient. That near-perfect ability to transfer energy without loss is the only reason our global power grid can even exist. They are truly the quiet, unsung heroes humming away in the background of our lives.
Okay, so everything we've talked about so far has been in the classical world, right? But what happens when you take this beautiful classical law and drag it down into the bizarre, weird world of quantum mechanics? Well, the amazing thing is, the principle still holds up, but it takes us somewhere completely new, right to the cutting edge of modern computing.
And here's the big, mind-bending leap you have to make. In our big, everyday world, magnetic flux seems totally smooth, right? It's continuous. You can have any amount of it. But when you get down to the quantum level, especially inside materials called superconductors, that's just not true. Magnetic flux suddenly becomes quantized. It can only exist in these tiny, discrete, individual packets. It's like finding out that a ramp is actually made of microscopic stairs. This is called flux quantization.
And that tiny packet, that indivisible unit of magnetic flux, has a specific value. It's a fundamental constant of the universe, just like the speed of light or the charge of an electron. It's built from other fundamental constants, like Planck's constant. And this isn't just some weird theoretical idea. It is a real, measurable thing that is the foundation for some of the most advanced tech we're building today.
So how are we actually using this? Well, there are these amazing devices called SQUIDs, which stands for Superconducting Quantum Interference Devices, and they use this quantization to measure magnetic fields with absolutely insane precision. But even cooler, in my opinion, are flux qubits. They actually use these individual packets of magnetic flux as the fundamental bits, the zeros and ones of a quantum computer. So yeah, Faraday's simple law of induction is now right at the very heart of quantum computing. And now the story really comes full circle, because we can bring AI into the picture. You know, solving Maxwell's equations to design, say, a new kind of motor or antenna is ridiculously complex. So today, we're actually using AI and neural networks to simulate and optimize these systems. AI can come up with designs for things like wireless chargers that are way more efficient than anything a human engineer could dream up. It's like AI is the next evolution in our quest to master the power that Faraday first gave us a glimpse of. So let's just take a step back for a second and look at the whole journey. I mean, it is just incredible. It starts with one guy asking a simple question in a cluttered lab in the 1830s, and the path from that question leads directly to the absolute bleeding edge of quantum computing today. That original spark of induction is still burning brighter than ever. And this really lays it all out. You've got Faraday's discovery in 1831, then you have Maxwell turning it into a universal law of nature in 1865, and now, today, we are using that exact same principle to build the quantum computers and the AI that are absolutely going to shape our future. It's a direct line. Which really just leaves us with one final fascinating thought. This single physical law has grown from a simple coil of wire into a quantum bit. It has branched out into technologies that Michael Faraday could not possibly have dreamed of. So, the real question for all of us is, what's the next branch on this incredible tree going to be? Thanks so much for joining us on this deep dive. As we said at the beginning, this explainer was based on the fantastic and detailed essay by Jorgo Schneeppert. If you want to learn more, we really recommend you go check out his work at schneeppert.de. Absolutely. Thanks for listening. Goodbye.
Goodbye.
Schneepat.de is a private project by Jurgo Schneepat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.